Okay, it is almost time according to the clock on this computer. So I'm going to load one more time the OChem one, and then also the GChem one for tomorrow. Hey, Jonathan. And again, going to ask a favor. If some of you guys don't mind, as people add in late, if you wouldn't mind occasionally adding in the just a handout for the day, that'd be great. Thank you so much. You guys are so awesome for doing that. Okay, actually, I lied. I'll load it one more time. And then we'll go ahead and get started on this. So welcome to another round of Forgotten OChem. I'm going to go on an assumption here, and that is that most of you kind of went through the motions in lab. That to a large extent, it was going in, having no clue what the procedure is, but figuring your way through everything you could, and then copying somebody from last year's exam or last year's lab. I'm assuming that that's what it's going to be. I missed you guys, but hopefully the Friday filler and the office hours sort of balance everything out. And oh, this is content. This is very much content. Yeah, so I probably should explain what happened schedule-wise. Thanks, 17 of you altogether ultimately responded. And it basically ended up being just a unanimous thing saying we needed to upgrade. And so the woman who's coming in to take over the bio, unfortunately, is out of the country until the second week of November, I believe. And so she'll be taking over. So in order to keep things, I guess, up to date or have something, I decided I want to do the lab technique lecture, because forever since we started this, spectroscopy was one lecture and lab techniques were another. You can't really do all of it in 2 hours. So moving it, like splitting it back up. So there's going to be spectroscopy and a little bit of lab techniques in the other one. And this will be just that other lecture. So basically it killed a whole bunch of birds with one stone. So it's very, very good in that sense. And so hopefully you'll hear from somebody named Emma in about, second week of November. And she'll be stepping in. Okay. So with that said, today, main thing I want to do is just discuss the techniques. I don't think so. I think she's just going to do new ones, but you can definitely ask her if she has, if she can do that, because I'm sure she can. And her take on things will be different. She actually did fantastic on the test from a very conceptual standpoint. She's got I just think, a really good way of looking at things. And so find out, I think she might be doing office hours before she's starting, but I don't know. I'll try to stay in that loop as much as possible. But for this, again, honest answer, how many of you for OChem Lab, you just sort of went through the motions? Yeah, it's pretty much what we all do. You just fake your way through it, write up the lab report, copying your neighbors, rounding up. Yeah, and it's just what it is. Oh yeah, you cited that it never worked and explained that everything just sucked. Yeah, and actually somebody privately, I'm sorry to laugh at this, but yeah, to actually go against the grain and say I enjoyed it. Yeah, it is kind of a private message because it's definitely going against it. But the labs themselves, you're actually some good stuff to learn from it. And because the MCAT is so lab-based, the theory behind it is something we should get down pat. So what I'm going to do is I'm going to take a little bit different approach. And that is, before I start into anything, just sort of ask you, yeah, there is a handout. If somebody, unfortunately, I already started lecture, but hopefully somebody can drop it in the chat box for you. So we'll see who the kind soul is who's collecting karma points. Oh yeah, there's also, lecture tab in there. Perfect. Okay, so hopefully, thank you for whoever's loading it up. And then, okay, so the big thing about lab techniques, let me actually step back for a moment and just ask you a random physics question. But when I talk about velocity, is velocity speed or direction? It is both. Perfect. Has speed and direction. Okay, that may not seem like it has much to do with this, but it's actually the most important concept we'll deal with for lab techniques. So for lab techniques, there's basically two things you need to do: purify and identify. And so I'm going to focus on the purification today. Spectroscopy, that lecture is going to be on the identification portion. But for purification, there's two types. There's general purification, where you take something that's like 50-50 and maybe make it 98-2. And then there's very minute purification, where you go from the 98% pure to maybe 99.9. And so in order to do this, if you have something that needs to be purified, you agree there must be an impurity in it, at least one, which means you have at least two compounds, possibly more, all mixed together. So in order to get purification, does one have to separate from the other? Does something have to move from one point to another? Sure. And therefore, that's where we go full circle back to motion has speed and direction. And so some techniques will involve different directions. So let me just consider the various phases. Which way does a solid move? So if I have a solid chunk of something, I put it on a flask and I wait patiently for a couple of days, which way will it move? Left, right, up, down, or it just won't move? So a solid won't move, or it's going to fall down just because of gravity, but generally it's not going to move. Okay, fair enough. Which way will a liquid flow? Up or down? Ah, so interesting. So we have the option of dissolving it. So let's hang on to that thought for a moment. But a liquid typically will flow from high pressure, low pressure. So it'll flow down from the gravitational gradient. And which way can a gas flow? Up, left, right, it can flow in all directions. Okay, so here's a concept. Let's say I have two liquids. They're mixed together. Do you think it's possible to convert one of those liquids into a solid and then let the remaining liquid flow down while the solid remains in a filter? Sure. Or would it be possible those two liquids evaporate and turn one of them into a gas and let a gas flow up and out of the system, leave behind the liquid that didn't evaporate? So we just have the core, the secret to all of our lab techniques. Simply change the state of matter so that one can move away from the other, and you're set. Now, Sophie, you brought up the fact you can dissolve something. So is that another thing to consider then? So we have solid, liquid, gas, but can we also have solute? Is that also a potential? Ah, so there's another one. So can I take, let's say I have two solids. Is it possible to have two solids, add a solvent, and have one solid turn into solute and flow into the solvent while the other one stays as a solid? Is that ever a technique they do? Sure. Ah, so it's the start of recrystallization. So it's the first step where you dissociate one into solution. You then filter out the solid and you crystallize it, turn it back into a solid. But most definitely. So every single technique we're going to look at, and every single technique you do, even in biochem, I want you to keep it as simple as, what is the thing that's moving? And am I separating by direction, i.e. changing phase? Or is there also something known as chromatography, where everything moves in the same direction, but just at a different speed? So for instance, let's talk about, let's say, column chromatography. Can I put a mixture on the top of the column, and will all the solute particles, everything in that solution, will it migrate down the column? So is that basically the way a column works? You load the top of the column, the solvent flows down. Ah, but at different speed, exactly. You're not separating by direction because everything's going down. Now it's speed. What about electrophoresis? You load everything at the cathode, all the anions, all the DNA strands, all the RNA strands, all the proteins, whatever you're dealing with, and do they migrate across the gel? Same direction or different direction when they cross a gel? Same direction, but what's true of their speed? Same direction, different speed. So again, if you can make this ultra simple and literally make it kind of a kindergarten perspective, one thing will move away from another. It's either going to be a phase change to try to get different directions, or you're going to live with the fact they're all in the same phase and it's a race to the finish line. And then, like you mentioned, does size ever play a role in how fast something will migrate? Definitely. So for instance, teach me something in biochem. I don't understand why, if I added SDS to a protein, that it would migrate faster across a gel. So please translate what I've just said. Not SDS, excuse me, beta-mercaptoethanol. Denatures of proteins. So breaks the disulfide bond. So instead of being clumped up into a blob, can it break into a more tubular thing and flow with less drag? Yeah, SDS makes things negative. Absolutely right. I tossed the wrong thing in, so I apologize for that. So hopefully it seems okay. So I've gotten ahead of myself, but the big picture, I totally am happy with this approach then, that we're going to separate things according to the direction they flow. And then also going to consider like size factors and various other things along the way. But so far, so good. Okay, so with that in mind, the thing that's popped up on your screen, I have no idea what this is and I need some help. So I'm on the MCAT, I click the page change, and I get a graph that has vapor pressure on one axis, temperature on the another, and they say something about distillation. So what the heck is going on here? And by the way, Tiffany, I forgot the comment. Absolutely perfect. Yeah, SDS incorporates a negative charge into a protein, so it gives everything the same mass charge ratio, makes it all go to the anode. So two species with different temperature requirements to reach a certain vapor pressure. Perfect. So according to this, I want to just revisit this graph for a moment. How many of you have ever boiled water? Let's say you're making water for tea, or let's say boiling water makes spaghetti. Somehow you have a pot full of water on the stove. How many agree it seems to do nothing, 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 and all of a sudden a few bubbles? After a few bubbles, it shoots up rapidly. How many have definitely lived this curve? Maybe you don't remember it from school. You certainly don't remember the Clausius-Clapeyron equation, but oh yeah, it always works when you're not looking. There's a few truths in life. The more you push the button at the elevator, the slower it comes. The more you push the crosswalk button, the less likely it'll change. And the more you stare at the boiling water, the less chance it'll actually boil. So Stephanie, you are genius on one of those three. Make sure you know the other two, and then your life will be complete. So, okay, so with that in mind, I have these two things. According to this, which one do you think boils more easily? The blue or the red? Blue, perfect. Its boiling point, and boiling point is defined when atmospheric pressure equals vapor pressure, which is why it terminates. You can only get up to atmospheric pressure because once you become atmospheric pressure, boom, you become the atmosphere. You're no longer liquid, you're no longer boiling. So this is the boiling point of the blue one. This is the boiling point of the red one. According to this graph, however, though, at the boiling point of the blue one, is there still a little bit of the red one that's also evaporating away? So if I have a mixture of two liquids, I'm going to get a lot of blue, but you're right, I get a tiny bit of this red, but that's still potentially a problem. I can't, if I collect everything, it's not pure blue, it's got a little bit of the red. Yes, and I got a question, and you're absolutely right. I should have mentioned that again. So up here, this is where the vapor pressure equals atmospheric pressure. That's why it terminates here. And that is defined as the boiling point. So the boiling point, I give you two definitions. So the first definition, the formal definition, the temperature at which atmospheric pressure equals vapor pressure. So can you tell me, is it easier or harder to boil things in the mountains? Not cook, but boil things? Easier. Easier to boil in the mountains because lower atmospheric pressure, which means you have to heat it as high. Harder at the bottom of the ocean, the flame always goes out. Every time I try to light a flame at the bottom of the ocean, it always messes with me. But yeah, higher the pressure, that's so annoying. But yeah, in the mountains, very low atmospheric pressure, so things boil more easily. But you can't cook as well. So why can't you cook as well? Fish friends are overrated. If you saw Nemo, tell me how well those friendships all worked out. Yeah, yeah. Quit boiling water down at the bottom of the ocean. Stick to land, dang it. But yeah, so when you're in the mountains, it boils lower temperature, so it takes longer to cook. It's like, is it going to cook faster at 110 degrees or 100 degrees? Yes, Jonathan, you've beaten the system. We could, in fact, bubble boiling water into an ocean if we wanted to. But yeah, so it's going to cook faster at 110 than 100. So if you're in the mountains and water's boiling at 95, you're cooking lower temperature, it's not going to cook as fast. Okay, so getting focused on this again, I'm going to boil this away, get a little bit of this impurity, and like Jonathan said, rinse and repeat. Collect what you get, do it again. So if it's a 10-to-1 ratio, for instance, then here's what I'm going to get. So let's say this is 10 times as volatile as this one, meaning if I get 100 torr here, I get 10. If I get 200, I get 20, 330, and so forth. So what I do then is, let's just say I start with a solution that's 1-to-1 blue to red. When I boil it at the boiling point for that, it's going to become 10-to-1 in favor of the blue. And then I condense it, collect it, and I have a 10-to-1 new solution. If I boil that one, what is 10 times 10? 100. And 1 times 1 is 1, meaning it's 10-to-1 to begin with, and it boils at a 10-to-1 ratio. So it's now 100-to-1. So now if I do it just twice, evaporate it, condense it, evaporate it again, can I get something that's about 99% pure, about 100-to-1? So how many feel that's reasonably pure? 99% is pretty dang good. You're going to have a hard time beating that. So for this one, because their boiling points were so different, it was easy to do. But what if their boiling points are close? So let's say we'll take the same red one as before, but now this yellow one, the boiling points are a lot closer to one another. So is the ratio still 10-to-1? Is this still 10 times as high as this? Good point. A lot of terminology. If I don't define a term, please ask me, because I've said vapor pressure and I've said volatile, and I've failed to define both of them. So first off, let's do this. What is vapor pressure? The pressure generated by vapor. Okay. You're not allowed to put the word in its own definition. So although that's totally right, sadly, Webster's wouldn't like it, but that's exactly what it is, the pressure due to the vapor. But formal definition, it's force per unit area, i.e. the pressure, generated above the surface of the liquid through evaporation. Okay, so it's basically how much it leaves the liquid, evaporates away. And then volatile. What is a volatile situation? Not an example one, but what defines volatile? Volatile is something that's about to explode, something to blow up. So a volatile solution is one that's about to blow up, meaning what? Unsteady, going to rapidly vaporize. Exactly. Any way you want to put it. For our terms then, volatile means it's going to rapidly turn from liquid to gas. So the more volatile it is, the more readily it's going to change phase into the gas phase. So the more volatile liquid, would that be something with a higher or lower boiling point in your estimation? More volatile, lower boiling point. Exactly. And so if two things have comparable boiling points, is it also safe to assume then that they have comparable volatility, evaporate about the same? Okay, so in your estimation, would it be easier then to separate two things with the same boiling point or two things with different boiling points? The bigger the difference in boiling points, easier it is to separate. Okay, so that means for this next one, I agree. When somebody said 4-to-1, I kind of say 4-to-1, but for whatever reason, my notes I put 3-to-1. And it's never a perfect ratio. So if we want to say 4-to-1, that's fine. But let's say we start again with the solution that's 1-to-1. If I evaporate away, let's say it evaporates in a 3-to-1 ratio and I condense it. Oh yeah, so less volatile means higher boiling point, more volatile means lower boiling point. So volatile is something that can easily evaporate away. And so if we think of something that can easily evaporate away, that's something with a low boiling point. So hopefully it seems okay. Perfect. Okay, so starts out at 1-to-1, evaporates, I condense it. How many think 3-to-1 is pretty good purity? How many are okay with this? Yeah, so let me actually, let me field this. So 3 to 1 is not very pure. And then the question in the chat box. So theoretically, is it possible to have distillation with 99% plus purity with 2 species with close and boiling point? If you're willing to wait a couple years, or if we do a cool little trick involving surface area. So yeah, you can technically purify anything from anything if given enough time and enough effort. But is life a choice of quantity or quality? I mean, how many would agree with that? You can get one of the best or get a dozen of the poor. So same thing here. If you're going for more and more purity, you end up using or losing more and more residue of what you want and leaving it behind, meaning you get a lower yield. So you give me any 2 things and I can get a 99.9% purity in that 0.000001 milliliters isolated from the ocean's worth of stuff I started with. So you can, the problem is every step you add in to purify, get a little bit more quality, you end up losing a little bit of quantity. And so that's always one of our choices, quantity as opposed to quality. Okay, so that in mind, 1 to 3, I condense, I evaporate again, 3-to-1 ratio of something 3-to-1, 3 times 3 gives me 9. 9-to-1, so after 2 cycles, I'm not as pure as I was after 1 cycle over here. So when the boiling points are far away, you don't need a lot of cycles, but if they're close together, we'd agree, dang it, I need to do a lot of cycles to get it back up to even close to 99%. Oh, I didn't just do that to you. I did. So I'm gonna have to go through all of it. But my point being, sorry, I'm gonna give you a second to screen capture. So my point being, if you end up with 2 cycles in a 100-to-1 ratio, that's great. The other one takes 4 cycles, and you're going to be somewhere around 88-to-1, which is, again, just under 99% pure. But would you agree it's a lot harder to purify when they're closer together? I mean, does that kind of make intuitive sense more than anything? So the closer the boiling points, so close together, far apart, big difference in relative vapor pressures, less difference in vapor pressure. As the boiling points get closer and the vapor pressures get closer, more cycles you need. So do you remember something called fractional distillation and something called simple distillation? Do those sound vaguely familiar? No idea what they are. So somebody teach me what exactly it means to do fractional distillation. And honest answer, how many are so far removed that, yeah, in chat, I've got 2 people say, I don't remember, I don't know. And that's part of it. How many have long since forgotten? So, okay, so something there. So I think difference in fractional has distillation column with more surface area. Yeah, okay. So I'm gonna go on the assumption most people forgot or didn't cover it, and that's fair, and that's something you have to assess for yourself. But somebody's put the word surface area in there, so I'm going to teach me, why would surface area matter? So weird question, but how many of you have ever taken a shower? A little bit on the personal side, but I think we're close enough we can answer this. No, okay, yeah, never. So hygiene is overrated. It just takes away from study time. But let's say you accidentally bathed one time. If you take a shower, does your mirror ever steam up? So how many have definitely had a steamed up mirror while taking a shower at some point in their life? How did this happen? The water was in the shower. How did it end up getting steamed up on the mirror? Vapor. So the hot water, because at whatever temperature, no matter what temperature's at, you always get a little bit of vapor. The evaporated water, steam spreads through the bathroom. The evaporated water, exactly. Water vapor travels through, and the mirror is cold. Exactly. So what happens when that warm vapor strikes a cold surface such as your mirror or your walls or anywhere in the bathroom? You are smart. That's why you should feel smart, dang it. So it sticks, it condenses, perfect. And then does it stay there forever? Is your mirror still steamed up or no? No, what happened to the vapor? The mirror heats up from the condensation and eventually you open the door and it flows somewhere else. Perfect. So did you just come up with the idea of evaporate and condense on a surface, re-evaporate, condense on a surface, re-evaporate? So can I take this exact thing you just said about the steam condensing on a mirror, then evaporates. Maybe it condenses in your bedroom, evaporates and condenses somewhere in the house. And it keeps on doing this from one surface to the next. So every time you provide some surface, you've provided a chance for it to condense. If you give it a surface, you give it somewhere to condense and then re-evaporate and re-purify. So Tiffany mentioned the word surface area. So why would surface area matter? We'll figure out where the surface area is, but the more surface area, would that be more or less cycles, would you say? More or less chance to condense? More chances to condense, perfect. So if you increase the amount of surface area, okay, it's also going to condense and re-evaporate. So you mean to tell me we have two advantages. We condense it, but also we give it an area from which to evaporate again. Perfect. So let's see if we can figure this out, how to do it in actual experiment. So I feel really good about the theory. So this is going to be simple distillation. This is going to be fractional. Okay, so I feel a little bit good about this. So now it's time to look at the equipment, figure out how the heck we set this up. Okay, so taking this picture, I have to somehow convert a liquid to a gas. How do you do that? So go back and help me out. So the question is, which was which? And so no, don't be sorry, because actually I'm going to be a jerk and make you answer it. So which one do you need to condense and evaporate more often? The left one or right one? The right one. And so that's when it needed more surface area, the right one. More surface area is fractional distillation. So you have to have more fractions because you have more surface area to have those fractions form on. So it's a weird term, but when you fraction something off, you're evaporating it, condensing it, evaporating, condensing, so you're taking more fractions of it. So fractional distillation, more and more times you're taking a fraction and condensing it, fraction of it, condensing it, fraction of it, condensing it, until you get it very pure. But again, quantity, quality choice. Okay, so far so good. So here's my distilling pot. Purple because red and blue combine to make purple. Spade because it's the best suit in all of cards. Actually, no, it's because the company that provides free pictures for me to steal from the internet, actually ChemDraw provides them, sponsored by that company, so I at least should plug them. If you go out and buy expensive glassware, always choose that suit. It'll suit you. Oh no, that should be their slogan. Anyway, here's my pot. How do I turn it into a gas? Heat it up, perfect. Should you heat the top, the middle, or the bottom? What's your intuition tell you? Heat the bottom. So for efficient heating, just in general, should you heat the lowest point because that's where it is coldest? Is that where you get the most effective heat transfer? Sure. Where should you put your air conditioner ducts? So if you want to make a really efficient system for heating your house, your building, your whatever, your air conditioner duct should be in the ceiling or floor. Always in the ceiling. That's why if you ever walk into a cold room, any of you who ever work in a cold room in chemistry or happen to work in a restaurant that had a freezer, you ever notice they always have ceiling fans, and right above the door, that's where the cooling unit is. Because after you have the greatest heat leak, and that's where heat rises. That said, where should you have your heating ducts? At the bottom. Perfect. Coldest air goes down. So most efficient heat transfer, the hot to cold is maximized if you have cold in the ceiling, hot in the bottom. Okay, so yeah, and then somebody mentioned how we heat it. So I'm going to say, let's just take a blowtorch or a flame. Let's heat just this one point. Good or bad call if I sit here with like a blowtorch and just heat that one spot? Oh, okay. Why do we heat the bottom? Naturally, heat rises or sinks. So generally speaking, heat rises. So if the hot rises up to the top, does that push the cold back to the bottom? And do I get a more effective heat transfer? But somebody mentioned, their teacher said, don't use a blowtorch, don't use a flame, don't use a heating iron. They said, use a sand bath. How many learn to use a sand bath? Why? Why a sand bath? Perfect. Uniform distribution of heat. You don't want to have a hot spot. You don't want something to go above the boiling point and bump. If you form a high temperature here, it heats up, gets in the surface, and it'll be above its boiling point and it'll explode. So you want to, number one, uniform heating on the surface. And number two, did they ever say to throw a boiling chip in? Yep. Does a boiling chip float or sink? Sinks to the bottom. So if you happen to heat the lowest point, is that where the boiling chip is? And does that provide surface area that now that can evaporate instead of on the surface here, can evaporate on the surface here, form a bubble and pop up? So how many notice when you put it there, you always throw a stream of bubbles coming up from it? It falls to, in theory, the warmest point that you're heating up and sucks up that heat. And the reason sand is used is because the sand transfer heat from one point to another in the sand bath. So if my sand bath is around here, is the sand going to heat up and spread it out so that I have a hot spot here, here, here? Can the sand spread the heat so that it's touching the surface? Oh no, I'm sorry. I just got a message in here and I probably should have asked this. How many took lab on Zoom for school? Kind of a really messed up, in fact, I'm thinking a much stronger word than messed up. So right now, my wife, I'm not, maybe you know this, but she's a chemistry professor. In this semester, she's been saddled with teaching a bunch of labs because she drew the short stick. And it's because literally nobody in any of her labs have any experience after a year off. And it's just interesting to watch the disaster that is stepping back into lab after a year from trying to do lab over Zoom. So I take it all of you had to watch videos of some professor spilling things into a flask, and ta-da, that's lab. So we can still get by, we can still do the theory of it, or simulations. Yeah, I mean, that's all it was. The FET thing is awesome, by the way. I mean, those simulations are fantastic and good, but oh, some poor grad student. Oh, you were total low budget school. Sorry. I mean, I don't mean to say that in such a mean way, but yeah, probably a state school. Yeah, yep. So we all got stuck with something. Okay, so the sand bath uniformly heats it up. It evaporates away. Is it a good design right now, or am I just going to lose everything? We're just going to lose everything. Would you agree? Heat it up and it's just going to be lost. So what do you need to do something? What do you need to do something to make sure it doesn't happen? Yep, wide open. So I've done a pretty bad design right now. So what should I do? Add a condenser. Need to start adding some pieces. So first off, I have to have the piece that changes its direction. Vapor comes up. Did any of you have a professor that made a huge ordeal about putting the thermometer at the base of this column so that you knew the temperature when it went over the side? So why did you measure the temperature here and not down here? So why is the thermometer up here as opposed to down here? And those are the nitpicky questions they love. Fond memories, huh? Okay, so in this one, perfect. You want to get the temperature of the vapor you're collecting, not the liquid you're boiling. So this is still a mixture. This hopefully is a little more pure. So you're getting the temperature of the vapor that's coming over the side, which tells you something about what's going to go here. Okay, so this is a little bit better. Yeah, I'm assuming all of you had a TA or professor who was pretty uptight about this. And let's just say it's a great test question if you're a multiple choice test writer for a standardized test. Gives you the temperature of what condenses. Okay, it's condensing everywhere, but what happens for the stuff that condenses in this column on the side here? So anything condenses here, anything here is going to drip back in, reboil, drip back in, reboil. But here, do you agree it's just going to go down the side? Okay. So, sorry, I'm just typing something. Okay, I have a cooling jacket here. I'm gonna hook it up and you tell me, did I do this right or wrong? And just to reiterate, I think somebody came up with this phrase. So you need to figure out what that actually means. But I'm gonna put the cold water in here and hot water out here. Did I just make my TA and lab professor happy, or did I screw this up? What did I do wrong? I made the professor mad. Why? What did I do wrong? Okay, but why? Please tell me why it should be flipped. And then also, while you're telling me things, teach me a few other things. Why are fish gills a certain way? Why is flow through the Bowman capsule around the loop of Henle, through the ascending and descending tubes, why is it the direction it is? Why are any of these things set up the way they are? Because I'm always confused by this. So what is the goal in fish gills, this cooling system here, and in the kidney? What is the whole goal between all of these? Concentration gradients, exactly. Gas exchange, heat exchange, particle exchange, anything exchange. So I'm gonna come up with two ways of doing this, and you tell me which one you think is gonna work out best for me. Okay, either way, I have hot vapor coming in. If I have cold on the outside, so I'm putting cold in on top, is there a temperature difference between hot and cold? How many degrees? Hot and cold are drastically different. So you are definitely going to get heat transfer. The inside is going to cool down to become warm. The outside is going to heat up to become cool. Still a temperature difference. You're still going to get heat transfer. But eventually, is this going to go to room temp? That's room temp. And then is any heat transfer all done? No more. Okay? As opposed to what we do here. If I have it cold at the bottom, then the inside can become cool. If the cold picks up enough heat from the cool, it becomes cool, but the inside can be room temperature. When it is flowing this way, oops, sorry, did not mean to do that, I meant to do this. When it goes this way and this way, temperature difference in the beginning, but is half your column being wasted with no temperature difference? Here, when I start cold at bottom, coming here and exiting as warm, do I always have a gradient? And do I ultimately get more heat transfer? Is the inside coming off cool instead of room temperature? So do I get more heat transfer with concurrent or countercurrent flow? You get more heat transfer because you always have a gradient with countercurrent flow. Is that the way the nephron works? Is that the way, I said Bowman capsule, I meant nephron. Is that the way the nephron in the kidney works? Definitely, you have a urea gradient. Is that the way fish gills work? Does ocean water flow across? And is there a countercurrent so it can pick up as much O2 as possible from the surrounding water? Sure, gas exchange, ion exchange, waste exchange, heat exchange. Any exchange is done better with countercurrent than concurrent flow. And so how many are familiar with that? How many does that sound reasonable to you? And does this picture help to make sense when you actually consider cold on bottom going on the outside? And so I should note, this is the outside up here, the inside, this is the outside, this is the inside. I'm going to put some pink line between it so we can separate the two. But you get overall more heat transfer when it's countercurrent. Okay, would they ever make a big ordeal about the placement of this and the direction of the water flow? Is that right up the alley of the type of questions they like to ask? Know the reasoning behind it, know if it's a common ideology. So those are the little things. How you attach, how you clip, and all those things, who cares? you'll either have to read the data table from the results, or you're going to have to consider why you apply heat here, why a sand bath, why is this here. So a lot of the what you do and be able to explain or interpret the results. Okay, so I'm pretty big on this. So I have this tube. Finally, when it condenses, the vapor turns to liquid. The liquid drips out. Ta-da! I have a pure liquid dripping onto my counter. Oops! Probably need a flask to collect it. One problem with my design, and I want you to tell me how to fix it, is when I'm condensing hot or cold. The liquid that's dripping out is hot, room temperature, or cold. Cold, anywhere between cool and cold that I'm collecting. If it's a cold surface, is there a chance moisture from the environment can condense on this and put water into my system that I just spent all that time purifying? Okay, so let me address that. So perfect. What can they ask about the cooling jacket? Definitely they can ask, do you put cold at top or cold at bottom? And then ask you why. And just the straightforward answer is you put cold in bottom. So number one, it fills completely. And number two, you end up with a gradient. You end up entering cold and it exits warm. So there's always a temperature gradient between the inside column and the surrounding jacket. Second, why do I put the condensing jacket here and not here? So what it does and where you place it. Those are basically the two reasonable questions they can ask. So why don't you place it here? Because if you did place it here, where would it condense? Would it condense and drip into the flask, or would it just fall right back in? Excellent question. I'm going to actually hold off. So I just got a private message about what's the name of this experimental technique. And I'm actually at the very end going to ask that as a question. So in fact, well, might as well do it now. So what exactly is this technique called where evaporate, condense, evaporate, condense? Simple distillation, exactly. So simple distillation is where I collect over here. Reflux is when I put it here. There is a technique called refluxing where you heat it up, condenses, and drifts back in. So if I put the column here, it wouldn't escape. It would just evaporate back in. And let me figure out, just going off on a tangent, that word reflux. How many have ever heard of something called acid reflux? What exactly is acid reflux? So I know I've heard it, and I know if I take a purple pill, apparently it gets better. Is acid reflux where you puke, or you puke and it goes back down into you? You regurgitate it up, it comes right back down. You regurgitate it up, comes right back down. So acidic fluids, gastric fluids, shoot up your esophagus, and then they drip back down, come up and drip back down. So reflux is where you put the condensing column here, so evaporates and drifts back in, evaporates, drifts back in. Why would you ever want to reflux anything? That makes no sense. So what would be the goal of refluxing? It's actually not purification. It seems like it should be, but it's a completely and totally different technique where, let's say I want to dissolve something into a liquid. Does it dissolve better at higher or low temperature? Higher temperature. So if I want to dissolve it, I want to heat up the liquid to, let's say, its boiling point. But if it boils, it's all going to escape. So what if I put a refluxing column right here, and it evaporated away, condensed, and drifts back in? Evaporates away, evaporates away, condenses, then drips in, then evaporates again, condenses, drips in. Is there a way to make this boil but not escape? So in other words, can I dissolve something into boiling liquid and reflux it so that it doesn't escape? So if in chemistry, in OChem, you ever see the word refluxing solvent, it means boiling solvent that can't escape. The column throws up, it goes up the column like the esophagus, hits the walls, drifts back in, evaporates, condenses on the walls, drifts back in. So it's a way to keep the solvent hot without losing it. Yeah, and refluxing is related to recrystallization. Exactly. And then flux capacity, excellent. Are you actually being serious about flux capacity? the flux capacitor from a movie? So I'm assuming, oh, it's a made up thing in a movie that they use to describe anything they don't understand. Oh, we better fix the flux capacitor. It's like one of those classic joke things. So if your TA was saying that, that basically meant they didn't know. Yeah, exactly. So Tiffany's question, do we reflux so we can heat it up and not lose as much yield? And exactly, because the problem is if the solvent escapes and crystallizes on the walls, so it's a way to keep the solvent maximized. Okay, moving on. So this is, as somebody mentioned, this is simple distillation because I didn't use much surface area. Okay, about to click on.
Hey, Todd, do you mind if I ask a question?
Yeah.
Sorry, not to beat the dead horse here, but so this cooling jacket here, I understand how like the maybe why the top one ends up with cold liquid at the end, but I'm not quite clicking why I would want that over the room temperature option on the bottom.
Oh, so which one is going to re-evaporate and be lost? So if it comes out at room temperature, it's higher temperature, it can evaporate and lose it. If it comes out cool, it's less volatile. So you save more if it comes off cold.
Got it.
So you
Okay.
take out more heat.
Got it.
Yeah. So it just, I mean, that's the whole purpose. Okay. For this one, I have this arrangement here. So now I need 1, 2, 3, 4 cycles. So where do I want more surface area? Do I want more surface area on the side where I'm condensing or the side where I'm evaporating and condensing? Yeah, so it's not so much that we want the flask to be cold where we collect it, we want the sidearm to be cold where we're collecting it. So the flask, yeah, you do want it to be warm enough to evaporate, but cool enough that it recondenses on this climbing part. So this is where you want your heat. But once it turns to a liquid, so let's say it goes up, let me just click in. So here's your distilling column. Is it longer and has more surface area? So same thing, except we now have a longer column, more surface area. We don't want this to be cooled yet because we want it to keep on being vapor, vapor, vapor. We really don't want it to cool until we're ready to collect it. So would you agree you're not going to collect it until here? And so this is where I want to keep a cold surface on the outside so that it's hot, 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 evaporates, 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 and then finally comes and condenses and collected. So if that makes sense, for the distillation process, and the mistake I made in the first one is I described 2 techniques simultaneously, and that was a bad call. Let me stick just to distillation. You heat it up here, it goes up. You can have a problem, and maybe this happened in your lab. Did anybody have a problem where you could see the vapor go up and then all of a sudden just sort of stop climbing? Because the room cooled the glass so much that it couldn't keep re-evaporating. You end up getting high temperature here, but the gradient went down. So did anybody ever have a TA that made you wrap this in glass wool? An insulating material, fiberglass of some sort? Yes, so I'll field that question. So okay, so hopefully it's clear on this one then. And then, yeah, so does the length of this column matter? What's your intuition? So the question was, does the length of this column matter, i.e. the surface area? Why would it matter how long this column is or if it's packed with stuff? So the longer the column or the more it's packed, what's true of the amount of surface area it has? Increased surface area, which means more or less of these cycles. Perfect. The more surface area, the more it can condense. So it's getting more and more pure each step of the way. But by the time it gets to the top, evaporates, recondenses, evaporate, recondenses, keeps on doing that. By the time you get up here, you have more or less than before coming over. Much less. So is this a quality or quantity decision I made by adding surface area? Quality. I get much more pure because it evaporates and condenses more times, but I get very little coming off. Lower yield, better purity. So you either get purity or you get yield. And how many like that simplified approach? It's either quantity or quality. And how many can buy into that? That is really one of those choices in life. Lab is definitely one of those. The more you purify it, the less you get. And is this always a dilemma in bio, where you're dealing with very expensive reagents? So in bio, you're analyzing micro purity. Chemistry, we might do milliliters. You were all the way down to micro. And so the same sort of problem we run into. Okay, let's try a question and see how it goes. So, 40 seconds, enjoy. Oh, sorry. Nice, fast answer. So I got 2 answers in chat that came up quick. So good call. So 3 right answers so far. 4 right answers. So I'm hoping my timing system is right. Wow, I think my timing system just got screwed up. So I'm going to try drawing on it and see if that'll work. Okay, I can draw on it at least. So I'm going to go ahead and start the answer. For whatever reason, the system froze up. So boiling points are close. So if they're close, what kind of distillation do you need? Simple or fractional if the boiling points are close? Yeah, you need fractional when they're close. You have to do something special. You need to get it into more fractions, separate it. You need simple when they're far apart. Okay, how do you make it fractional distillation? You increase the surface area. Perfect. Okay, so let me get rid of my weird scribble. So boiling points are close, need fractional distillation achieved by increasing surface area in the distilling column. So how many agree exactly what we did? Increasing the distilling column will work. So surface area goes up. So that's true. And then will increasing the length of the cooling jacket have any impact? Or is that too late? It's already been condensed and everything's over? So this one makes no sense. That's not going to do much. Well, adding glass beads in the middle of the column. Did any of you have a professor that made you do that? Fill the column. Adding surface area. That will also work. So that makes surface area go up. And this one is if your professor is about 1 million years old. Many, many years ago, they do that. How many was this just a big question mark for you? Yeah, what would, actually good question. What would increasing the length of the cooling jacket do? It'd make it tip over and break. There'll really be absolutely no purpose to making a cooling jacket any longer. So you basically, the length of the cooling jacket is long enough to cool it down with not making it too heavy to make the glassware system unsafe. So reality is longer cooling jacket wouldn't do much of anything really. Okay, in copper mesh, how many when you look at copper mesh would say, huh, what? So interesting, depending on if you're a chemist, copper mesh is what they used to use for distillation. Anytime you find anything in literature, copper, like reagents, so for instance, you can add 1,4 to a carbonyl using cuprates. Any cuprate chemistry was because people screwed up in distillation. So this is an amazingly cool historical thing where they use copper mesh for surface area, thinking copper was inert. ends up it wasn't, and they discovered reactions by making mistakes. So I just love that sort of story. Okay, so question, because cooling jacket surface area doesn't affect purification, you are thinking exactly right. That is exactly the thing. You want to have distillation, condensation, the column going up, more surface area. Once it's condensed, it's pointless to have more. Yep. So why is it right above? Because that's where above the column, it's condensing, re-evaporating, condensing, re-evaporating. Once it goes over and it's cooling jacket, you want it to evaporate or just stay condensed once it's on the side. So once I've gone up and over, and now I'm collecting it, in this area right here, I want to keep it condensed. So that's why I put my condenser over here. This is the evaporation condensation region. Once it goes over the side, condense and collect. So condense and drip back down, condense and collect. So I want to do, if I want to purify it more, I make this region more surface area, not this region. Okay. So perfect, best answer. B is in, boy, everybody got it. So that was a cool thing. You can probably still go to doctor school, but you won't be able to make your own reagents to give to patients. So yeah, you'll just have to hire somebody to make all your solvents, but that should be okay. And you will be ridiculed and probably have to wear a hat and sit in the corner, but you know, it's still doctor school. And just so you know, doctor school has a K, not a C. You'll get a solvent guy. Everybody needs a guy. I want you to explain something to me. The other day, I was hanging out with my friends and we're cool. We're just really cool people. So we sag, meaning our pants, like we hang them low and so the bottoms like scrape on the ground, but it was raining. And as we're walking, what happened to the water from the rain and my cool saggy pants that were dragging on the ground? It went up my leg, exactly. It migrated up my leg. And I just, like a paper towel, exactly. And it happened to be, this is really weird, but I happened to have just walked by some salt water. And I didn't even notice the salt water rising up my leg. You couldn't see it. But later on, when my pants dried out, I had this salt residue. And my friend said, oh my gosh, you have chromatography pants, and the RF of that salt is 0.61. What was my totally cool chemist friend saying to me? What's meant by chromatography pants? I don't get that phrase. What were they saying? Oh, the imaginary person in private chat just told me they were thinking that your pants are a polymer. They're made of cellulose, they're made of cotton. So they're a cellulose product, it's a polymer, and that the solvent will migrate up the polymer and it will drag solutes with it. That is exactly what I was just thinking. So how many would agree chromatography is just that? You send solvent up some polymer and particles get dragged along with it. We can't just say polymer and solvent. Instead, do we use phrases of stationary phase and mobile phase for the solvent? Sure. So whenever we talk about chromatography, we have the following. So if I add a nonpolar solvent and I add it into a beaker like this, and I'm going to put my solvent way up here, and you tell me, is this a TGL moment? Is Todd going to lie? Dang it, lying to you. Because if I did that, would the spots go climbing or would they go swimming? No bueno. They'd go swimming, wouldn't go where you want. So where do I need to put the solvent line then? I kind of don't want to go swimming, so I only want a little bit of solvent. I put the solvent maybe around there. Perfect. You're welcome. Enjoy your day. Okay, so is it going to go up like the paper towel, like my pant leg, like this piece of silica gel. Ah, so you had the TA or the professor that was really anal about it and said it had to be exactly 1 centimeter. How many had that professor that had an exact distance? And the reason they gave you an exact distance is because you were more anal about all your measurements. And the reality is, as long as it's below the spot and you can't get too heavy in solvent and drip down, 1 centimeter is pretty much a standard. So it seems reasonable, but the solvent's going to go up. As the solvent goes up, what's the spot going to do? Is it going to go with the solvent up the plate, or is it going to stick to the plate? Or is that totally dependent on the spot? Depending on the spot. So if they did this, which one had the highest affinity for the plate? Red. Which one had the highest affinity for the solvent? Blue. And what's an RF value? Ah, the ratio of the distances. Yes, 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 yes. I didn't think anybody would get that. So perfect. So how much the spot traveled divided by how much the solvent traveled. I should always let the solvent go all the way to the top, yes or no? No. Once the solvent reaches the top, it can't go any further, but the spots can keep going, screws up. So about 80%, exactly. You want to, again, you want to leave about 1 centimeter here and about 1 centimeter there so you don't get that drip. I don't really have a good mnemonic about the solvent being polar or non-polar. Usually because the solvent can be a mixture, the plate itself is silica gel is polar. So that's when I would implore you to remember is that silica gel, alumina gel, the material we use, the plates we use are typically polar plates. So if I have a non-polar solvent in a polar plate, then what's true of this blue dot? Is that blue dot probably polar or non-polar? Non-polar, because it traveled with a non-polar solvent and did not stick very well to the polar plate. Whereas the red one is probably polar. Exactly. So if I said one of these is phenylalanine and one of these is aspartic acid, which of the 3 spots you think would be phenylalanine? Blue. Perfect. Exactly. Which one do you think would be aspartic acid? Red. Sure. Charged, polar. So perfect. So can I suddenly make this a biochem experiment if I really want to mess with you? By all means, foreshadowing for the end. Yeah, so the reason why again, so the plate equals polar, the solvent equals non-polar. So what is going to rise the most? Something that sticks to the plate or doesn't like the plate and goes into the solvent? So this one should be non-polar because it's more like the solvent. And then what about the red one? Didn't rise very much, so it's more like the plate or more like the solvent? Should be polar. And then the question was, phenylalanine, benzene side chain would be non-polar one, aspartic acid would be your polar one. Those would be your best educated guesses. So perfect. So what's going on in this experiment? This is really weird. The same spot went up the greatest amount. This is actually one of the things that I remember when I learned this in OChem lab, I was pissed. I didn't think it would go that way. And then when I ran it every time, I didn't believe them and I did it and kept on going the same. Non-polar is still traveling the farthest, but not as drastically different. And the reason being, which is a stronger interaction, the compound with the plate or compound with the solvent? So I got mixed reviews so far. Okay, so the votes are in mostly plate, because when the plate was polar, the polar stuck. When the plate was polar, the polar stuck more than the non-polar. So this one's going to like the plate and the solvent both. This one hates the plate and hates the solvent both. So this one bound, so this binding of the plate must have been more than the solvent could pull it up. The indifference of the plate must have allowed it to just go along for the ride. What you didn't notice in this one is this could finish in about 10, maybe 15 minutes at most. This one would probably take 20 to 30 minutes to get them to climb, because nothing wants to go. So it's just the overall comparison of distance, not time. Non-polar doesn't stick to the plate, so it goes higher. Polar. So the interaction with the plate is more important than the interaction with the solvent, which means we use the same plate consistently. But did you ever have professors that made you change the solvent? You might start with hexane and finish with ethanol. So anybody actually have a professor that made you do that? Start with one and gradually convert it into another? Yeah, so why did the non-polar go so far? Because it did not like the plate, whereas the polar liked the plate. So the polar kept on sticking to the plate even though the solvent tried to pull it along. This one, the solvent is really pulling it along, but has no interest in staying on the plate. So it just sort of gets caught up and travels with it, not really liking the solvent or the plate. So it just goes along for the ride. This one likes the plate more, so it sticks more than it moves, if that makes any sense. So the key thing, take home message, non-polars go farther on either scenario. And so we usually use a silica gel, a polar plate, and the solvent can be anywhere from non-polar to polar. Okay, big picture. This is an identification technique. I'm going to hit clear in about 3. You're screenshotting 2, 1. Column chromatography is next. This is a big one because is there just a whole field in biochemistry where you start screwing with the column, making the column something that has, let's say, histidine residues on it, or an ion exchange column where you have a bunch of positives on it or a bunch of negatives on it. Or maybe you put like an antigen on the column. So starting with plain run-of-the-mill column chromatography, we're going to do the same thing, only instead of having it climb up a plate, can I take the same stuff that was on this plate, the silica gel, can I put it into the column? Can I put the same spots instead of at the bottom? Can I put them at the top? And instead of the solvent adhering to the plate and climbing, can I just have gravity pull the column, the solvent down the column? So which one do you think is going to come off this column first? Red, green, or blue? Why blue? So you're absolutely right. Why? Less attracted to the silica gel. That's why it climbed up. So the same reason it's going to go down. So perfect. You mean whatever made it climb here is going to make it go down faster there? Perfect. So I get the separation. Notice red and green lag behind, blue comes off. So what you probably did in OChem lab is once the blue came off and the nonpolar solvent was taking forever, did they say start adding a little more of a mixture? Instead of pure hexane, make it 50% hexane and 50% ethanol. So did anybody have a professor that made you change the solvent as you did it so you weren't there all day? So let the non-polars come off first. Once they're off, then start making the solvent a little more polar so that it speeds it up. Okay, conversely, if I use a polar solvent, they don't migrate as fast and you don't get as good a separation as before. Okay, so you're still gonna have your non-polar come off first, but these are really close. So which solvent would be better to use? So if I wanted to separate these 3 things, would you A, do non-polar the entire time, B, polar the entire time, C, start with non-polar and gradually make it more polar, D, start with polar and gradually make it non-polar? How many did I just totally lose, by the way? So clearly I didn't lose any people. You guys totally nailed it. Exactly. So if I did just pure non-polar, I get the first one, but these 2 take forever. If I do non-polar, I don't get good separate, or polar, I don't get good separation. So if I use nonpolar for a while to get this one off fast and get a little bit of separation here, and then add in the polar to speed up the process, just to kick them off the end. So we'd start with nonpolar to isolate this one, get these a little bit separated, and then polar to pull them off faster. Hopefully this seems okay. Last but not least, this little gold area is sand. What is the purpose of the sand? Not so much a filtrate, but exactly. Somebody said to make the column flat. You want the silica gel to be uniform and flat as much as you can, because you want the starting point to be the same here, 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 no matter where this material is on, you want to travel the same distance. So the problem is when you pour solvent in, if I pour solvent into the system, can it start stirring everything up? But if the sand is there, if it hits the sand, so what? The silica gel will still stay flat on top. So they sometimes call this an impact buffer, meaning when you pour the solvent, it hits it really hard, gives it an impact, it keeps it nice and flat. Okay, question time. 3 questions, see how you do. Give you about 30 seconds. Okay, so I just ran into my first problem. I felt like I totally knew the material, felt pretty good about it, in fact. And now all of a sudden I'm realizing I don't know what some of those words mean. I don't know what elution time is. I don't know what an RF is. So somebody help me out. What is a elution time? And by the way, everybody who's tapped in, yes, you've all gotten it right. How long it takes for the compound to clear. So the solvent is going down the column. As it goes down the column, eventually it's going to drag the material. How long it takes to leave the column? Exactly. So that tells me how fast it's going down a column. So if it goes down the column really fast, that means high or low elution time. Very low elution time, exactly. It's not going to be on the column for very long. What about RF? RF tells me how far it travels compared to the solvent. So if it goes up the column very fast, will that give you a large or small RF? So if it goes up the column a lot, you agree it's going to have a large distance. So let me just again do these 2 terms. So RF is distance the spot travels divided by distance the solvent travels. So if it goes up the column a lot, you have a very big RF. If it goes down the column fast, you have a very small elution time. So as RF increases, that means the distance per time increases. That means it's going up further, so it must be going up faster. And then for RF, RF is distance, whereas elution time, the faster it goes, the less time it takes. So basically, as one goes up, the other one must go down, if that makes sense. RF means it travels fast up the column, so it's going to travel down column fast, faster it travels, less time it takes. Meaning, best answer, C is in cool. So everybody who submitted, you nailed it. Okay, next. This one give you about, I don't know, 10 seconds total. Perfect. First answer in right. Second answer right. Third answer right. Perfect. So why are all of you saying 0? Which is more important, interaction with the plate or the interaction with the solvent? interaction with the plate is the most important one. How strong is the antibody-antigen interaction? I forget, is that a very weak interaction or is that about as tight as it gets in bio? Very strong interaction, perfect. Meaning, is that antigen going to bind that plate and never migrate anywhere, no matter what kind of solvent you add? So to break that interaction, you have to do something extreme, change the pH, thermal denaturing, add another antibody to compete, so a mobile antibody to compete with the one on the plate. Or in this case, I'm sorry, mobile antigen instead of the bound one. Good, perfect. 0, it's not going to migrate. And finally, last one, give you about a minute. Last one's the hardest question of all of them. Okay, so we'll see how that goes. Use your instincts. Okay, so this is one where you just have to trust your gut instinct about your math comprehension here. So if the RF is 0.6 as opposed to 0.2, what can you tell me about the relative speeds? Perfect. So if RF goes up, elution time goes down. We know that. So if time goes down, it's going to be in an earlier test tube. What is meant by an earlier test tube? This is what I don't get. So what am I actually doing? When I do this column, don't I just let it drip out onto the table? Or do I collect the first fraction, and then the second fraction, and the third fraction in subsequent test tubes? So how many did this and you get one test tube at a time? First one, second one, third one, and so forth. Okay, so here's the reasoning we're going to use. If I consider 0.6 compared to 0.3, is it safe to say, or 0.2, excuse me, is that a factor of 3? Is this going 3 times farther than this? Is 0.6 3 times 0.2? Sure. So one of two things I can say. I can conclude that this is 3 times faster, or I can conclude this is going to take 3 times longer. Does that make sense? If it goes 3 times farther, it's 3 times faster. And this one's going to take 3 times longer. So perfect. So Sophie, which one is it going to come out in? So if this one came out in number 6, this one's going to come out 3 times later. Perfect. About 18. Because it's, so let's just do it this way. Let's just say we got 1 test tube per second. So the 6th test tube, I'm going to say time equals 6 and RF equals 0.6. So the ratio is going to be 0.2. So this one should be higher or lower, the time. So I'm just going to try to set up a table here. So this is 1/3. So this one must be 3 times. Basically saying if it's 1/3 as far, it must be 3 times as long. And it's interesting. So when you say that, how many feel that same sort of way? Like, oh my gosh, that this is easier now. Once you see an answer, that's the way a lot of this is going to work. Is this a case where you could learn from doing the question more than you can learn from reading? So let me go back up. So somebody proposed a method of y 0.6 over 6 equals 0.2 over x. Why that doesn't work? Because basically what you're getting at is, if I look at this number, in order for this to be equal, does that one have to be smaller or larger than 6? So if the numerator got smaller, you're making this one smaller. This one applies when it's direct relationship. What you actually needed to do with this, if you want to do it math-wise, set up the exact opposite way. They're inverse relation. So it should actually be x over 0.2 because it's inversely related. So see if that ends up telling you anything. And I mean, I need to figure out what exactly I'm solving for in that case. But does that make sense? And this, by the way, is a ton of math. But it ends up, I've inverted it, but yeah. So although this will work, I think the intuitive, 1/3 the distance, 3 times the time, I think is just a better way to do it just visually. Factor of 3, one goes up, the other one goes down. Okay, chromatography is going to pop up again down the road, so I'm going to skip to this for a second for the sake of time. I'm going to erase what I've put up there. I'm so sorry. So 3, 2, 1, clearing. So now I can go with this. So it's 1/3 migration speed. So 3 times long to dilute. So it comes off instead of the 6th one, it comes off in the 18th one. Yeah, so, okay, so perfect question. So exactly, it went 0.6 in the same amount of time, the other one only went 0.2. So does that mean it's gonna come off, it's traveling 3 times as fast? So which one's gonna get to the top of the plate first? It's traveling 3 times faster, exactly. Yeah, 0.6 is gonna get to the top of the plate faster. It's also therefore gonna get down the column faster, 3 times faster. And that, hence 6 as opposed to 18, the 3 ratio. Okay. Third technique, gas chromatography. This one, I'm going to blow off the early part. I'm going to focus more on the questions going to pop up. But basically, the gist is this. If I have a container here at around 200 degrees Celsius, sounds good, I'm going to inject my sample in, samples here. At 200 degrees or higher, it's going to vaporize. And if I have a gas moving along here, and I use helium gas, because helium gas is highly reactive or helium gas is inert. Helium gas is inert, so it doesn't catch fire. Do you agree? If I put O2 in there, it'd be spectacular. I get O2, big flame here, I get explosion here, some fire out the end. It'd be fun to watch, it wouldn't help me. So I use an inert gas that blows through. It's called a carrier gas, just carries through. This is your so-called mobile phase. And then I fill it with candle wax. I mean, in all reality, it really is candle wax. If you've ever seen a candle burn, is it a solid, a liquid, or kind of somewhere in between as it melts and reforms, melts and reforms? I mean, how many describe a candle as it's burning? There's some liquid, there's some solid, and it's kind of a mixed bag of all of it. Perfect. So the gas takes forever to bubble through, drags along, but it's going to drag these particles with it. It ends up, some stick to the column, some pass through, but when they get all the way through, they get analyzed in this container. So I'm going to inject my sample in, going to have the carrier gas, my PAT column, I'm going to detect it. I'm just going to read collisions. All it reads is when the gas finally makes it out, hits a detector, detector shoots up. So no reading, no reading, no reading, spikes up. No reading, no reading, no reading, spikes up. Spikes up when things collide with it. So here's what I care about. I'll go back to the picture in a second. I want to look at this as a complete learning question. So have I messed with you with the x-axis on this one? Actually, let me just give you about 30 seconds, 40 seconds, we'll talk. Okay, so just to give you a heads up on what I've done, I've screwed with you. I changed the retention time axis, and there's a method to my madness. If you've been in a lab in the last 25, 30 years, they always have time going one way. But up until the mid 80s, time ran the other way because the machine used to be a digital output. A piece of paper literally rolled out and it read this way. And so they kept it that way for the longest time for consistency till finally IUPAC got together and said, yeah, let's screw it, let's run it the right way. So I did it this way just to make you pay attention. So first one coming off, second, third, and fourth. And you know what? There's no reason to notice it because it's so weird, but just want to point that out. I don't want me to make you extremely paranoid, but I wanted to just toss it out there that this is the one technique that I really hope you pay attention to the x-axis because there's a convention change from years ago to nowadays. So this one, which is the highest concentration? So first off, tell me, reading the data, which one do you think is in the highest concentration? Peak 1, peak 2, peak 3, or peak 4? As I've labeled them. So let me label this 1, 2, 3, and 4. How many read peak 1? Why? Area under the curve equals quantity. So the area under the curve is directly proportional to collisions. Collisions are directly proportional to the number of particles. Perfect. So this is my most abundant compound. Is it the one that came off first, second, third, or last? Last. So your TA or your professor might have said, and technically it's not exactly true, but it's totally the way to do this, is that this is based on boiling point. So how many other professors said boiling point, first boil is usually first one off, last boil is last one off? It's technically the one that binds the column the most, takes forever to come through, but they're right in the sense is that the same things that affect boiling point. If a compound is lighter, is it going to travel through the column faster? Yes, and is it going to boil sooner? Yeah, lower molecular weight boils more readily. If the compound is polar, it'll stick to the polar solutes dissolved in the wax. So polar compounds take longer to come through because they bind what the suspension in that column. So generally speaking, then this one would have the highest or lowest boiling point. Highest boiling point, perfect. So now the question is, which do you expect to have the highest boiling point? So as far as these go, you'd expect 5-carbon alcohol, 3-carbon alcohol, 5-carbon alcohol, or 7-carbon alcohol. They're all alcohols, so they all have hydrogen bonding. Which one do you think will have the highest boiling point? Perfect. Why D? So why D? Heaviest, exactly. So they each have the same amount of hydrogen bonding, each have the same polarity, but highest molecular weight, heaviest one, is going to be the hardest to evaporate. Branching and most carbons, exactly. So this stuff you get, and is it much easier to think of boiling point as opposed to anything else on this? Yes, it's not perfect. 99% of the time it'll work, but technically it's affinity for the column, but boiling point is great. Yeah. How many agree with exactly what Uniga put in there? More carbons, more effort to boil or melt. Both of them. Both of them are totally true. Melting or boiling are both true. How many agree with that? Heavier things, more carbon makes it heavier. Heavier is just harder to evaporate. Exactly perfect. Your logic is 100% spot on. So keep that same reasoning. Okay. Oh, so it's not, okay, so this just happened to be that. The highest boiling point is the one that takes the longest time to come off, and that happened to be the one with the greatest area. So area has to do with how much you have. And so the reason we said it's peak 1 is because, is that the one that was the thickest, the tallest and the thickest peak? Is that the one with the greatest area? So this one I had a lot of, second most, maybe third and fourth most. So this might have been 50% of the mixture based on the area, and it just so happens to be the last one coming off. So there's no correlation between area and when it comes off. Those are two independent events. So area tells me how much of the mixture it is. And so from this, I'm gonna assign some numbers and you tell me if this is true. So I'm gonna say this is around, let's say 46% of the mixture, okay? I'm gonna say this one here is around 20, no, my math isn't gonna work out. Let me make that around 17%. And then the other two I'm just going to fill in as needed, but this one might be, let's say 16%, so 33, 21%. Are those numbers close? So good question. Is peak 1 cyclo with 5 carbons, or is it pent with 2-methyl with 7 carbons? So the question was proposed. Oh, no. These aren't respectively. These are random. So this ends up being, this is peak 1 because it's heaviest. This is peak 4 because it's lightest. And then cyclo is a little less sterically hindered, so it's a little bit easier to get through. So it'll come off a little bit sooner. So that'd be 3 and this would be 2. So yeah, so that they're not listed sequentially. Sorry about that. I have no idea. I think I just did it to match the way it was delivered in the question. Okay, so random distribution of compounds, you had to identify which was which. So how many are kind of okay with this? This makes some semblance of sense. Oh, boiling point. So let me private question for the exam. Should we concentrate on the affinity of the vapor to the column or boiling point? Pretty much, and just a quick survey, how many had a professor, again, that said, base it on boiling point? 1, 2, 3, 4, 5. So, okay, I would say go with boiling point, even though technically this other one, because that's what everybody does. Oh yeah, so the question is, should we look at it in terms of polar and non-polar? Not for this one. For this one, it's all about boiling point. So the GC, usually because you have a polar column or polar suspension, the same things that make the boiling point go up are the same things that would make it more polar and travel slower in the column. That's why they say look at the boiling point, because boiling point is going to be a spot-on predictor of what you get. So when you said polarity and boiling point, by looking at boiling point, we've already sort of accounted for polarity. So it's sort of already built into that way we're looking at it. Oh, the kinematics or kinetics of the, so the question is, the book tells us the kinetics of a compound. I think it might be a typo if it says that it should be the kinematics. Kinematics is how easily something can move. So through the column, which can move more easily. And it's the one with the lowest boiling point. And then also steric hindrance, this one can move more easily than something with more branching. Hopefully that seems okay. All right, jumping into the last of the techniques I want to push on you, and that is, computer's taking a second to kick in, acid-base extraction. This one, I think this is one of those that it's kind of a big picture thing. So step by step, I'll figure out, but basically I want to do the following. I have a mixture of 4 different compounds and I want to pull them out of solution. I'm going to do this by giving them a choice. You want to go into the nonpolar or polar solvent. So what do you expect the ketone is going to do? With long R groups, let's say, will this have a tendency to go into the polar or nonpolar solvent if given a choice? Nonpolar, perfect, because it's an alkyl. It's got a tiny bit of polarity, but mostly long alkyl chains. Same thing here. This one might belong to our group, nonpolar, maybe polar, but probably nonpolar. Probably nonpolar, because that's more important. And depending on R, probably nonpolar. So basically, this is a really bad experiment I'm doing. But what if I got really wild and adventurous and made that O minus instead? Now suddenly, will one of them want to go into the polar, the aqueous layer? Okay, so although all four seem to have a preference, their coefficient for separation and partition coefficient would say organic, 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 but as soon as I made it negative, now all of a sudden, can I take 3 organics and put 1 in water? So that's exactly what we're going to do. We're going to add all 4 of these to an oil, a lipid, an ether, some organic material, and some water. But in that water, I'm going to put a very weak base. And I make it slightly basic, which means if I make it just basic enough, can it take off the more acidic proton here? And so 3 of these stay in the organic layer, 1 stays in the aqueous layer, except I don't have the original compound. I have this negative compound. Yeah, so we call it the aqueous layer, but yeah, it's just water. But it's water with base in it. So I should just say, instead of saying it's just water, I should say it's basic water. It's mildly basic water. So water at pH, let's say 10 or so, 9 or so. So it's going to pull this proton off and make it go into solution. Okay, then I'm going to protonate it back and filter it out, and ta-da. Ooh, good question. So the question's been proposed, is it only base I can add? Is this specifically for base? What if instead of adding base, what if I would have added an acid? What would have happened? Good question. So I chose base because that was the first thing on the shelf, but let's say your shelf first thing was acid. If I would have added acid, would that have changed the results? Sure, if I added acid, do you agree it would have protonated and made that one a cation? So if I had acid, instead of taking this compound, could I have taken that compound, made that one more water soluble? So although I called it acid-base extraction, am I actually doing base acid extraction? I don't want to say both. So the statement that's just been proposed is, so aqueous layer could contain both acid and base. I want to change that to the aqueous layer could contain either acid or base. You can't make a solution acidic and base. It can't have a pH of 9 and 5 simultaneously. You can either make it 9 and get rid of this one, or maybe make it 4 or 5 and get rid of this one. And it's up to you. It's your choice which way to do it. But traditionally, they usually add base first. I don't know why, but you could have easily added acid first. But now, back to this. The important thing, the absolutely important thing that you have to know, and this is going to carry over really well into biochem, are carboxylic acids acidic. Their pKs are generally around 2 to 5. Phenols, like tyrosine, around 10. Protonated amines are around 9 to 10, like the amino terminal. So just so you know your pKs, but difference is this is positive, these are neutral. So technically, an amine, let me get rid of everything. This is acid, acid, and base. Okay, so if I add that, I'm next going to add a strong base, deprotonate here, isolate that one, collect it, add an acid. And so the sequence of it, I did bases first, then acids. You could have eaten acid first and base. You're just taking them out one at a time by adding something to make it an ion. Ions become more water soluble. So these 3 stay in organic, this one's in the water layer. These 2 stay in the organic, this one's in the water layer. This one goes organic, this one goes water layer. So you now collect it. This one you separate, and this one you distill away what's left. How many are okay with this technique? How many agree this is kind of like, I don't know, it sort of makes sense? And I mean, the reality is, does it seem like there's not really that much to it? Like, what the heck could they ask? The basic concept is you want to, one by one, turn whatever you can into a water-soluble compound by making an ion while not touching the other three. So you're pulling them out one at a time. Because remember, motion is direction or speed. They're all in the solvent. They're all in the organic layer. I want to turn them into something that will move into the water layer, but one at a time. So for an acid, I add a base. For an acid, I add a base. For a base, I add an acid. Here's what they can ask. So if you want to screenshot it, 3, 2, 1. So I'll catch up with you in just a second. Ah, perfect. You guys are nailing it. So the problem with acid-base extraction is acidic water sometimes a reactant? Can acidic water screw things up somehow, some way? Yes. Hydrolysis, that is your big concern here. So I'm hopeful, for whatever reason, my screen is not doing what it should do. There we go. Okay, so what we're gonna get is the following. This is an acid anhydride. And again, I want you to go through this process, the magic water line. Whenever I have a carbonyl with a potential leaving group, I can hydrolyze it. The O or the leaving group gets the H, this gets stuck with the OH. So if I was trying to isolate an acid anhydride using that technique that involved acidic water, what's going to happen? I don't get the compound. I actually react with the compound. So is that a general concern in lab? Do you want to make sure whatever material you're using, whatever process you're using, that it doesn't react with the compound? So just like we didn't want to use oxygen as a carrier gas in GC because it will blow the whole thing up, you don't want to use acidic water for water-sensitive compounds. So ketone, not all water-sensitive. Phenol, not water-sensitive. Secondary amine, not water-sensitive, but an acid anhydride without water, water-sensitive. Oh, so the question is, how do we know which we can attack? It could be either one, because the symmetry could break here, it could break here. I chose, generically speaking, the equal argot. So let's say it's a CH3 and a CH3, then it wouldn't really matter whether I broke here or here. But the O is attached to 2 carbonyls, and you could have broken either one. Yeah, it's actually their guide. So I would start with the following: the AAMC Guide to the MCAT. And what you'll find is they list what is and is not tested on the MCAT. It's not a perfect list because some things are more general. But for instance, things like angular momentum, angular acceleration, angular inertia, not tested. So it's you can look up stuff like that. But you will see like springs are tested. They list name reactions and kind of generic, but they sort of hint at it. Hydrolysis, because it's so prevalent in bio, definitely a name reaction you should know. Things like the Bear Villager has been tested before, Grignard has been tested before, aldol definitely. A reaction like Chichi-Bobbin. How many don't even remember what the Chichi-Bobbin reaction is, let alone maybe even heard of it? Yep, never heard of it? Don't bother learning it. Have you heard of aldol? Have you heard of Grignard? Have you heard of hydrolysis, decarboxylation? Know those. Anything that, in fact, any reaction that actually has an enzyme named for it in biochem, by all means know that one. That should be the obvious. In Zoom University. Yeah, So yeah, but the Chi-Chi-Bond reaction, I guess, Nobel Prize winning thing, nobody ever knows what it is. So don't waste time if something seems really obscure. Do the things that are common. They will give you, on the MCAT, anything that's obscure, they will present to you. Okay. So the last of the techniques, shifting away from OChem and more into charge-based techniques. Why do they call it electro? I have no idea. Why is this word electro there? Because that sounds very physics-like to me, and I'm confused. Uses electricity, uses charge, perfect. So any charge-based species in this world, do you agree it's because it gained or lost an electron? Is that a pretty safe assumption? Electrons are light, you can move around. So whenever you say electro, probably owns electron movement. Ah, perfect. So thank you. So Sylvie, is that guide that WMC gives away you can just download? I'm assuming that was just popped up. Yep, exactly. That's the exact same thing. It's a pretty hefty document. You have to read through a few pages, but eventually you'll get to the list of what the topics are that are tested. Yeah, exactly. Of which you probably are only going to need about 20, 25 of the pages, but you should always double check anything you're studying, double check there, do I need it? And sometimes it's not always crystal clear, but it's pretty good. And they're pretty straightforward and honest about what they put on there. Okay, so charged species is going to migrate from electric field. Anions migrate to the anode, cations migrate to the cathode. Neutral just sits there and just hangs out. Help me out, what again is PI? I know I've studied it, but I just can't remember what PI is. Isoelectric point, which is the pH at which it has no net charge. It is neutral. Does that mean it's charged or uncharged? No, there's a difference. So is it difference between saying charged and neutral and uncharged? Ah, perfect. It's charged, but neutral. Equal number of positives and negatives, exactly. It is internally balanced. It's a Zwita ion. It's balanced. If the pH is lower, the pH is more acidic, it's going to protonate things that become cations. pH is higher, deprotonates it, make more anionic. Okay, so fair enough. So if I wanted to get everything to migrate in the same direction, would I want them to all be the same charge? So let's say I wanted everything to migrate across a gel in the same direction and make it a race to the finish line. So everything goes same direction, but different speed. Then should I make them all different charges or the same charges? Let me rephrase that. Sign, same sign of charge or different sign of charges? So not magnitude, but just this case sign. Want to make them all the same sign. So earlier, somebody mentioned if you add in SDS, how we learned that adding in SDS, it's a detergent that incorporates into the protein and it gives it sulfate charge, sulfate's negative. So does it make all the proteins negative? And so just let's look at the logic. Let's say it's the 60s and you're a biochemist and you're sick of screwing up your gels and loading proteins and having them go in the wrong way. So could you take a lead from what happens with DNA and RNA? What charge does DNA carry? What charge does RNA carry? Negative, phosphate backbone, negative, exactly. So you have no issues. DNA you load, anions go to the anode. So no problem. I load it away from the anode, so it migrated across to the anode. RNA, same story, DNA, same story. But proteins, you read, could be positive, negative, or neutral. They have a little fluctuation. So if I throw SDS into it, do I now kind of make it just like DNA and RNA? I build in, instead of a phosphate, a sulfate. So instead of having phosphate, so you have sulfates on it, but is it still negative and it's still going to be the same story? So that now I don't keep screwing it up and loading it the wrong way. So do we do it this way? Do we try to make everything negative when we load it to have this uniformity? Basically, do we make it, for lack of a better word, idiot proof? So that we all load in the right spot and it migrates the right way. Okay, feeling pretty good about this. So, little orphan Annie, fat cat, anode is connected to what plate? Anode to anode or anode to cathode? Anode's connected to a cathode, exactly. So if this is a cathode, this plate is an anode. This is an anode, this is a cathode. Electrons flow alphabetically from anode to cathode. So I have my plates built up as follows. Here's my cathode, here's my anode. So where would the wells in electrophoresis go? The middle, the left, or the right? Where would you load in this case? What's your prediction? What's your theory? Load near the cathode, because again, we're loading anions. Anions go to the anode. So if they're going to go to the anode, would be wrong. So help me out here. What if I loaded everything right here? Let's say I put all my wells here. Anything wrong with that? It barely has any distance to move before it hits the wall, so it's barely going to move. The good news, would you be done really fast? Would you be out of lab in a few seconds? Loaded it, turned it on, all done. I'm going to lie in my lab reports anyway, so actually in that sense, it's brilliant. But unfortunately, your PI will hate you, but you don't care. You're out having fun. You're not stuck in lab, so at least you're in a good mood. So terrible decision to load there. So we load over here. If we load in the middle, just want to have this picture, anions go to the anode, cations go to the cathode, 0 in the middle. We don't actually middle load. Now it's just to say where things are going to end up. So because negatives are going to go this way, my wells are going to go right there. Okay, clicking in 3, 2, 1, and bringing back this chart. Absolutely imperative you know the C terminal, N terminal, and the 5 amino acids that can carry charge. So do we have gels at 1 pH? Let's say we make the entire gel pH of 3. Is that true? Or do we make it sometimes all 7? Or do we sometimes have a gradient? In fact, do we often have a gradient? How many degree? There's many different flavors. Some will have a consistent pH across. Some will have a gradient from one end to the other. It might be high pH at one end, low pH at the other. Does that seem okay? I mean, do you agree there's different ways to set these things up? And so I have to pay attention to the pH. So if I were to choose a pH of, let's say, 7, so if I was to load at 7, 7 is higher than these. When pH is high, things will get deprotonated. So the carboxyl terminal will be negative, almost always is. Side chains of aspartic acid, glutamic acid will be glutamate and aspartate. Histidine will be neutral, so we can ignore it. And then lies are his, be positive. Okay, so I kind of have to keep that in mind. Luckily, when I deal with any sort of charge-related thing in biochem, I pretty much only have 5 amino acids to care about. Why do I not care about cysteine? That does have a pK. Why am I not worried about it? Disulfide linkages, okay? You might, under certain circumstances, if you reduce it down, have to worry about it. So it's up to you if you want to include it. And then tyrosine, I also don't put in there. And this one's borderline on my perspective on it. Its pK is around 10.1. Chances of dealing with an experiment at 10.1 or higher, probably not going to happen. It still might have a condition, but by and large, we deal with 7. So I generally ignore tyrosine. So I have 5 in here and I'm going to worry about things as we go. Okay, physics. Oh yeah, pH was 7. I'm so sorry if my writing was piss poor, but yeah, so pH of 7, that's why I put that line there. So, and that's why I was looking at pH higher than pK or lower than pK. 7 higher than 2, 3, 6, and is it lower than 9 to 10 and so forth? No problem. The net force acting on something, you agree, is the sum of the individual forces. In an electric field, the charge times electric field strength, i.e. the plate charge here, and the distance between is going to set the electric field, and the Q has to do with whatever I load. What is meant by a drag force? Not sure what that means. So what's a drag force? What's wind resistance? Okay, it does definitely have to do with viscosity. Absolutely positively true. So a drag force, just in your mind, would it be easier to run through air or run through Jello? Please say this is theoretical. If it's a real, if you can answer this for real, not interested. But theoretically, easier to run through air than gel. Yes, and exactly. Somebody said, is it a backwards force, if you will, slowing it down? So sure, so if I load everything here, and let's, again, double check. Little orphan Annie, there's my anode. Fat cat, my cathode. Anode connected to the cathode. Cathode connected to the anode. Anions migrate to the anode. And again, I'm doing electrophoresis, so I play the anion game. So anions are going to migrate this way. So if anions are migrating this way because of a QE, a charged electric field force, does that mean the drag force is always pointing towards the left? Oh, so the question is, why do I call it Little Orphan Annie and Fat Cat? Because when I was a kid and when my kids were kids, and I'm assuming, therefore, when you were kids, they did that movie or the play or musical or whatever it was, Little Orphan Annie. And it's like, I hope it's something that crosses different generations. And so Little Annie and Fat Cat were two characters in that show. So is that a movie and or show you've never heard of or never seen? Because you're probably better as a person if you haven't. So anyway, I'm basing it on that. So if that helps. And actually just, oh, you have seen it? Okay. Oh, so you don't remember her being Little Orphan Annie? So the little kid was Little Orphan Annie, so Little Annie. And then the rich person who adopts her is the fat cat. So fat cathode, little anode, Little Annie, fat cat. Anyway, it just works for me. If you have a better way, by all means do it. But that's kind of what I use it for. So anode's connected to a cathode, cathode's connected to an anode. We're going to migrate this way. But the drag force. Somebody mentioned viscosity. Jello has high viscosity, hard to move through. What is going to be the most important factor moving through it? So do some shapes get through it easier than others? So if I had a protein that looked like this, as opposed to one that looked like this, would they have a different difficulty getting across that gel? Okay, so which one's going to have a harder time getting across? This one, the blob, is going to run into more stuff. Viscosity is going to slow it down more. This one, less. And so I'm going to change from the phrase surface area to what we're going to call contact area. I'm going to make it more of a physics concept, but their size is going to matter. So would you agree this component is very size related? So basically, can I separate things based on charge and or size? Are those the two properties of a protein or a DNA strand or RNA strand, whatever it is, that I can exploit to see which one migrates? Okay. This is, I got to go off on a tangent. Somebody just brought this up. There is a discrepancy between biochem and physics that always pops up. In physics, they call the anode negative and the cathode positive because they're based on current. A battery discharges current. It pushes electrons from anode to cathode in this direction. So if electrons are flowing from here to here, the absence of electrons start building up a positive surface. The accumulation of electrons start building up a negative surface. So if I asked you, is the cathode positive or is the cathode negative, what's the right answer? Which one is it? It is both. If you ask a biochemist, they'll go, no, 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 cathode's negative. Ask a physicist, they'll go, no, 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 cathode's positive. How many like me are stressed? So there's a reason I dodge this question, and that is because it is science specific. Is it the voltage source pushing the charge, or is it the field that's based on the charge? Stressed. Shit, this is like easy for them to mess with me. they're actually pretty cool about not messing with you. The reality is you have to remember a few things. No matter what these are called, positive or negative, as far as gel electrophoresis, as far as the field is concerned, cations always go to the cathode, anions always go to the anode. Doesn't matter what science you're in, what you're looking at, that's universally true to both a physicist and a biochemist and a chemist. So I sort of ignore the charge of the plates because I get stressed and freaked out about it, and it doesn't help me. I know anions go to the anode, cations go to the cathode. And I now feel really good about the fact that that's all I'm going to care about. Yes, exactly. Focus on the concept of migration and don't worry too much about the charge. So no matter what they do, still chant anions anode, cations cathode. And in biochem, do we make life easy by making everything an anion? We glue a bunch of SDS to a protein. We use things with phosphate backbones like RNA and DNA. We load anions here. They load at the cathode. They migrate to the anode. Anions go to the anode. So I'm good to go. So therefore, I no longer have to worry about direction. I've solved my direction problem. Now I worry about my speed. Bigger the charge, faster it's going to migrate. Bigger the size, slower it's going to migrate. So does everything migrate because of this mass to charge ratio, size to charge ratio? And therefore, I have different techniques that exploit different things. I can exploit the charges, or I can exploit the sizes. Like right here, do we exploit the size? So if it's okay, I'm going to erase everything on the screen right now. So 3, 2, 1, clear. And now I want to do erase. So I still want to say size for drag, charge over there. Those are your two features. Which one do you think is going to migrate across the farthest? Blue, green, or red? Well, yeah, smallest, but which one's the smallest? The blue, the green, or the red? No idea. Either I'm on crack and I'm asking a ridiculous question, or I'm messing with you. So I'm messing with you. I can't tell you anything now. I can tell you after the fact. Meaning, is this something I'm going to interpret the results later and work backwards? Yep. So I'm going to do something called isoelectric focusing this time. So what I'm going to do is I'm going to focus on Q and not size, because I know nothing about their size, but if they're all roughly the same size, then they're going to migrate accordingly. I'm going to load everything here, high pH, so everything's going to start as an anion. They'll migrate accordingly. So anions are going to migrate to the anode. So they're off and running. Here they go. Why did this one stop? Why did this one decide to not keep going? Because it's really big, or because something happened to its size? Or I mean charge, excuse me. Ah, you mean it actually stops because what's its charge at pi? 0. Perfect. So it migrated until it reached a point, started out as an anion, migrated, and then suddenly it stopped because that's its pi. So can you tell me which one of these most likely contains Lys his? Blue. Perfect. Lys his make the pi higher. Which one's most likely, or which color most likely contains glue asp? Glutamic acid, aspartic acid. Red, perfect, exactly. I'm responding to a private answer. And then which one is probably pretty much neutral, just a bunch of hydrophobes? Green. Keep in mind, PI is usually in the 5.5 to 6.5 region unless you have Lys his or glue asp. So this simply can separate by charge. Rich in Lys his over here, rich in glue asp over here, rich in whatever else. So hydrophobic, non-polars. So does this seem okay? So can I separate? Yeah, so why do the basic ones not travel so far? What happens to the basic ones? They start off with a side chain. So let's consider the 3 sites. The N terminal, positive, C terminal, negative, and then the side chain, positive for the blue. As it migrates over, what's going to happen? It's going to eventually migrate to the point where all of a sudden and actually let me go backwards because I've jumped ahead of myself. At pH of 9, this is going to be negative, neutral, and neutral. So it's an anion. When it migrates to here, eventually what's going to happen is you're going to get to a point where N, C, negative, R might take on a negative charge. Is that true? Even though I've lied to you again. So as it migrates across, is it going to start picking up protons? Because as you move across, the pH is getting lower and lower. So as the pH gets lower and lower, you're going to start protonating. Yep, exactly. So yeah, they do. And so my numbers are a little bit off. So this one I'm guessing is probably histidine because the PI is around 7. Had it been arginine or lysine, it would have been somewhere over here. And in fact, if I used lysine or arginine, excuse me, I'd probably pick the wrong buffer system and I'd have to make it higher. So depending on what you're doing, I might have to load it at 10 or 11 in order to get this to work. But I chose a system where I loaded around 9 and went to around 4. Pretty small window of pH, honestly. But I start out with this, where the C terminal is negative, the N terminal is neutral, and the R is neutral and migrates over. And this one, it might have not been that one that was positive. Maybe it could have been this one that's positive. So, but either way, whether I get those two positive, or that one positive and that one negative, or that one, this one here positive and that one negative, as long as I get to the point where it's a Zweiter ion, net charge is 0, so it's just going to stop there. Ah, perfect. Okay. So this is called isoelectric focusing because it migrates until it focuses on its isoelectric point. So what is the purpose of this experiment? I'm going to tell you the following. You tell me true or false. This tells you whether a protein is large or small. True or false? Large or small? No, it doesn't, because we didn't have any migration. Todd's going to lie. Exactly. TGL. So we did it based on charge. Okay, second question. This experiment tells me if I have more phenylalanine versus more alanine. This can help me distinguish whether I have alanine or phenylalanine in the compound. True or false? Nope, not going to help me at all with the nonpolars. Could be anything. But can this one tell me whether I have a lot of glue and very little His? Can tell me if I have a lot of arginine and very little asp? Yes, it can tell me about the charged amino acids present in the compound. It can basically tell me the PI. Okay, and then want to just be complete. Cations go to the cathode. So I want to just almost, dang it, my thing's freezing up again. Shoot, for whatever reason, I think I've overloaded the information on this. Okay, so I can do that. Oh, there we go. Now it's finally kicking in. So cations go to the cathode, just irrelevant in this one, but just want to be complete and keep on saying that. Okay, interpreting the results. I'm going to give you some results. You tell me what happened. Notice I've screwed with you. Before I did 9 to 5. Now all of a sudden I'm doing 11-ish. Like let's say I load around 10.5 and have it able to migrate all the way down to maybe 3.5 or so. So the pH gradient still is like this. Did I load them in the right spot or did I screw that up? So are the wells in the right spot for this one? Can't remember. So you're gonna have to teach me something. Do I load it when they're anions or cations? I can't remember. Do I load gels full of cations or anions? I load in a bunch of anions, SDS proteins, DNA, RNA. So when are things anions? At high pH or low pH? High pH. So I'm loading them with fellow high pH. I'm good to go. I have it loaded in the right spot. As they migrate down, I'm going to ask you a couple of questions. You tell me. Which of the following compounds, let's say it was a tetrapeptide, was made of glycine, alanine, phenylalanine, and threonine? Compound 1, the red one, compound 2, the green one, or compound 3, the blue one? Okay, I got 2, 2, green 2. Perfect. Why do you say that? No glue asp. No lies are his. So around 6, your hydrophobics, or your non-acidic, non-basic, neutral. Perfect. Compound 2. Which compound carries the greatest negative charge when the compounds are initially loaded? Why the red? Why 1? You guys nailing it again? Travels the farthest. Perfect. The one that's most an anion is going to go most to the anode. Perfect. This one barely went. And then also, you're a physicist. Perfect. The greatest QE. The one with the greatest force is the one that was able to migrate the farthest. Greatest QE could have only been greatest magnitude of Q, because they're all in the same electric field. Greatest Q, most negative. Perfect. And then finally, one more question that hopefully, oh man, not sure why this is. I think I'm having some Bluetooth competition all of a sudden. And hopefully it'll eventually freeze up or unfreeze. Okay, I've tapped this thing about 8 million times, so it might clear up. Yeah, and actually somebody said, would it be wrong to think the red because of the pH? So which one? Oh shoot, I hope it doesn't completely mess up. But for this one, sure. This is one richest in glue asp because it's the one with the lowest PI, and those be the negative ones. So that's valid. What does K6E mean? I have no idea what this secret language is. Can somebody teach me what does K6E mean? Mutation. At amino acid number 6, irrelevant on this question, but 1 point, I changed from K to E. What is K? Lysine, perfect. One of the lies are his collection, so it's a positive one. And I switched to E. What is E? Glutamic acid. So did I take compound 3, did I replace one of the positives with a negative? Oh, interesting. So yeah, it ends up, let me just toss it up here. Glue asp, because glue asp, glutamic acid, aspartic acid would create a lower pH, so they have low PIs. Lies are his, the basics, would create high PI. So if you think about it that way, that may help grouping together. And then just the way it's drawn, if you have a glue asp, you're going to sit down and get stuck here. So I don't know, that's a really bad analogy, but maybe that'll help with that. But glue asp goes down, they're the ones that take on negatives because they're deprotonated, more anion. And so for this question, this will certainly help me. If I were to replace the lysine with, in this case, a glutamic acid, would one migrate more down the plate, the same amount, or less? What's your instinct tell you? It's more anion. Anions go to the anode. It's going to migrate down further. And you would agree it would go down more. Perfect. Okay, so good on that. Ion exchange column. I'm going to go through this real briefly. This is going to be covered in the biochem lab, but I want to emphasize, is this based on charge or is this based on size? So just to emphasize, I'm interested in electrophoresis, just want to toss this out for a brief moment, but just like we have a technique to separate charge moving across a plate, we also have charges on a column. So what's going to bind this column? If it's negatively charged column, and I don't really care, carboxymethyl is one type. I don't care that you know that. I care that it's negative. Cations are going to bind, anions are going to elute. As opposed to an anion exchange column, if I put a bunch of positives, exact opposite, anions will bind, cations will elute. It's going to refer to this then as an anion exchange column. But just keep in mind, and again, future lecture, just introducing whetting the appetite to say, if we can use electrophoresis to separate by charge, we can also use columns to separate by charge. Yeah, so this, you're going to see this in the bio book mostly, but there's actually a tiny, tiny, tiny reference in the amino acid section in the OChem book as well, just real brief. Okay, and then good question. Can you explain how either of these, you asked for this one, I'm going to say either one of them would change if I change the pH. What would happen if I raise the pH of this column? Would the column more likely stay positive? Would it get more positive, or would it start becoming a neutral column? So if I were to raise the pH of the column, if I were to put down something that was higher pH, would the column stay charged, or can I actually start losing the charge on the column and releasing things? So in other words, will the charge depend on the pH? And that's basically what this is getting at, exactly. So if I add a high enough pH, I can deprotonate the column, make it neutral, nothing sticks. If I lower the pH enough, take all the negatives and make them neutral, nothing sticks. So is that actually one of the strategies for releasing it from the column? Usually we salt it out, add a competing ion, but can we also denature the column, if you will? Yeah, but so the question was, won't the column and the solvent be charged? Sure, but what does this care about? Does it care about the solvent or the column, the one that's bound? Is it bound to the solvent or bound to the column? It's bound to the column. So I don't care if I change the solvent at all, because this thing doesn't care about the solvent. I've changed the one thing that matters to the compound. I changed the column. Yeah, but again, and I don't, the target molecule, I don't care about it. I care about what it's binding. I've made a personal choice to release it by changing the pH and making the column neutral. But you're absolutely right. Could I have changed the pH differently, let the column the way it is, and change the compound? So in other words, can I adjust the pH higher or lower and screw with one of them? So if I have a negative compound and a positive column, then if I lower the pH, then I'm actually going to mess with the compounds, make them neutral, and they'll fall off. Or if I raise the pH and I denature the column and make it neutral, they're going to fall off. Either way, if you have a plus and a minus bound, if I change pH higher or lower, I'm going to mess with one or the other. Raise the pH, I'm going to mess with the positives. Lower the pH, I'm going to mess with the negatives. And somehow, some way, a negative positive attraction, if one of them goes neutral, there's no more attraction, it releases. So yes, we can change the pH, and how we change it, up to the experimenter, up to the conditions. So does that help or make sense? The whole idea is an anion is binding a cation in both of these scenarios. One case it's an anion column, cation binding. One case it's a cation column, anion binding. But if you change the pH, you can mess with either the anion, the column here, or the compound here, or the cation here and the column here, and you're gonna mess with it. Yeah, you create elution. So binding is because it's a salt interaction, ion interaction. The minute you get rid of one of them as being ions, there's no ion attraction, it doesn't bind anymore, so it elutes. So you're creating a neutral thing. Yeah, typically, and that's what I've hopefully shown is an N-terminal, C-terminal, and side chain. But yeah, this is generally because technically you could use it for other things, but it ends up sort of pointless because they're usually so massive. We have size extraction, it's going to be better. And then DNA and RNA is negative to begin with, so you would only be able to do it on something like this. And it just so massive it's sort of a pointless technique. We're going to use a slightly different technique for that one. Anyway, this was just a side note that charge can come into play. So next, electrophoresis. You're welcome. So last electrophoresis we're going to talk about, this is one we're going to separate by size now. So instead of worrying about charge, so what we're going to do is we're going to incorporate SDS. Is SDS nonpolar or polar? Which one? Amphipathic, exactly. It is both. It has a nonpolar tail and a polar head. What are proteins? Are proteins polar or nonpolar? Polar, nonpolar? Which one? They're also amphipathic in both. Meaning, can something that is both incorporate into something that is both? Makes sense? It linearizes it. I'm going to say it also denatures it. And the biggest thing it actually does, it gives everything an overall negative charge. But tell me your instincts. If the protein is really small, can it incorporate a lot or little? So protein small, less SDS. If it's bigger, incorporate more SDS. So my thought is this. If a protein is twice as heavy as another protein, protein 2 is twice as massive as protein 1, it makes sense that protein 2 is twice as long if it's twice as heavy. It's a guess. It's not perfect, but it's close. So twice as much SDS. Perfect. So it is twice the mass, but twice the SDS. So does everything then end up with the same mass to charge ratio? This is what it also does. It's going to denature it, linearize it, as you mentioned. It's going to get rid of the globular nature and make it more linear. But just as important, the mass to charge ratio. Bigger ones have bigger mass, but they have bigger SDS, so the Q goes up. Because they all have the same mass to charge ratio, they separate by their size. What's your instinct tell you? Smaller goes faster, smaller goes slower. So the question is, what's the difference between size and mass? How much space you take up and how heavy you are. So for instance, if I have a metal rod and I have a balled up piece of paper, the metal rod is tubular, high mass, but not very, not very big, if you will. It can move through in a way. A balled up blob of paper, much lighter, but more size. So size is really what we're interested in. The cross-sectional area, how much does it interact with that gel? Okay, so the last thing we're gonna do, again, where do we load everything? So now I've changed the question. Everything migrates to anodes, so we load everything at the cathode. Little orphan Annie, little anode connected to the cathode. Load to the cathode. Fat cat connected to the anode, migrate to the anode. So which one's going to migrate the farthest? Yes, size exclusion chromatography is inverted. So I'm not going to address that. I'm just going to address this one for now. So which one's going to migrate the farthest? In this case, yeah, so you're thinking of size exclusion chromatography. This is one. Smallest is going to go the farthest. Which one's smallest? Don't know. So you can guess. We'll make it more like a sporting event. Up to you. Which do you think is going to be the smallest? Go ahead and bet. You have no idea, but how many are betting blue? How many are betting green? How many are betting red? So 1 red vote, 2 red votes. Wow, everybody's going for the red. Interesting. Let's see how it goes. And there they go. Oh, what was the smallest? Green was the biggest. I know, it's like a random guess and you still feel like you've been messed up and cheated. But, okay. So can I safely say this one was the smallest because it went the farthest distance. It had the least drag. So which one is feeling the greatest viscosity? Blue, green, or red? Which one is going through the thickest medium? Trick question. The gel is uniform. Same viscosity. The only thing that's different, now it's going to lie, trick you as well. True. The only thing that's different is this is bigger, so it interacts. So one of the questions that popped up earlier, if we were to add beta-mercaptoethanol at the beginning of the experiment, what impact would it have? Why would reducing the protein have any impact at all? Makes it longer and thinner. Hot dogs go through tubes better than balls go through tubes. So it would travel farther, exactly. So would they ever, crazy as this would be, would they ever say, we did this native and we did it under reduced conditions, and give you both experiments and make you conclude which one has the greatest percentage of cysteine in it? In fact, how many might have had a biochem professor that has made you do that question multiple times in life? They have no creativity. Professors have zero creativity. And so the things you see repeatedly in school become the repeated things you see on the MCAT, same people writing it. So last of everything to mess with you. So smallest, largest, and middlest. So let's say you get some massive thing like this. I have no idea what southern blotting is. I have no idea what native page is. So somebody teach me. What is native page? So snowdrop, like that. I don't know if southern's for RNA, because I think, I could be wrong, but I think northern with all those R's and N's is RNA. For some reason, I thought southern. Oh my gosh, I can't spell. Thought southern was for DNA. And then proteins on this over here somewhere. I think that's something like that. And then snowdrop. Tiffany, explain snowdrop to me.
Can you hear me?
Yes.
Yeah. Yes. Yeah, exactly what you wrote, like that.
So what does that mean? I don't get it.
Oh, so S is southern, so right below southern you have D, so that's for DNA, and then N for northern blot, and that's for RNA, and then O it cancels out, and then W is westerns for proteins.
Ah, perfect. Seems like a pretty damn good mnemonic. How many have already seen snowdrop from a professor, a really good TA? Oh, really? So very cool. So Tiffany, thanks for tossing things out there, because spelling like my poor spelling plan works for me. I think your method is better, but whatever way works. Okay, so native page, polyacrylamide gel electrophoresis means we haven't added anything into it, probably dealing with a protein. Southern blotting means I'm dealing specifically with DNA. And I should probably spell it then, southern, even though that didn't help, but snowdrop, perfect. So here are the things I don't know. I have no idea what the heck is going on in that craziness. What the heck is this one? A ladder? Is there a fire? Why would I need a ladder? What do you mean by ladder? Ah, for comparison. You mean to tell me I throw every possible thing I can find in lab, like a chair, a napkin from the sink, maybe a broken faucet cap, maybe a few pieces of RNA, DNA, whatever I want, toss it in there and see how far they all migrate and come up with some idea of how big they are. Ah, fine. So I only toss DNA, no kitchen sink. Okay, fine. But do I toss in one or multiple strands? Maybe a kitchen sink is okay. Perfect. I toss it in there and they migrate. And I think they start up here, they migrate down. And notice the anode and cathode aren't labeled, but I do know if they start up here, the lower one must be the anode. Anions migrate to the anode. Perfect. So I'm going to tell you this one right here is really, really big, and this one is really small. Does that qualify in the telling you the truth or lying again? Did I do that right? Dang it, Todd's going to lie. What have I done wrong? Explain to me what I did to screw that one up. Lying as always. Complete opposite. Small things migrate far, big things barely migrate. So is this just nothing more than a reference? The so-called ladder is just something to compare to. So a few questions and see where we're at. Why does the unlabeled column have such a large number of spots? Control. You want to make sure you get every mass you can. So maybe this is like 2 kilodaltons all the way up to maybe 20 kilodaltons, or maybe 1 kilodalton to 10, maybe 50. You want to set a ladder to match what you're looking for. Sounds good to me. Okay. Which one contains the smallest DNA strand? So apparently this was southern blotting after all. Why do you say 1? Went the farthest. Seems easy enough. Last question of the day. How can you explain what happened in 3? I don't know if anything major happened in 3, but was 3 a very pure or not so pure sample? Not so pure because maybe something broke. Maybe you had a dimer that broke into 2 fragments. Possibly. That'd be kind of weird, but something weird could have happened. Or maybe you just didn't purify it and you had 3 strands. So for whatever reason, you have 3, you have pure, oops, something else was in there. Am I safe in assuming you read enough of these to be pretty good at looking at this? Or your mini prep sucks. Yeah, basically you were crap in lab. That could also be it. So this was your neighbor on the left, neighbor on the right, and you. Or me. But hopefully it seems okay. Anyway, this covers it. This is the lead-in. It's going to build in. There's a full lecture on biochem lab techniques, a hop, skip, and about a month away. So this is kind of the whet your appetite, and it fills in because there isn't enough OChem lab techniques to fill the lecture, but clearly I piled on this and went overtime. I feel really confident, really good because you guys knew this stuff so well. So I'm assuming your biochem knowledge is actually pretty solid. No, thanks. Nice. I appreciate that. But yeah, and again, just sorry that it went over, but this is it. If you have any questions or need me to go back to a slide, let me know. But you are free to go about the world and find these things. Homework wise, do the OChem homework, save your bio homework. You guys are very, very welcome. Appreciate it. Again, as always, thank you for your positive attitude. Oh, thank you. It's sweet to say. So thank you guys. Yeah, so I'll go back to crystallization. So somebody's asked for crystallization. Oh, enjoy your work meeting and have fun. Hopefully it's nothing but good stuff.